So we're ready to start a new topic, which is using series to help solve differential equations. Now, a better mindset to have is not using series to solve differential equations, but using the first part of the series, a polynomial approximation, to get a good approximation to solutions. So let's think back about what we learned from calculus. Now, the first idea in calculus is that flat things are a good approximation for not flat things, and in particular, tangent lines are relatively good approximations for functions. That is to say, if I have a function f of x, it looks like the tangent line plus a bit of error. Now, how do we make the error smaller? Well, we use more information about the function. And in this case, that more information means another derivative or maybe multiple derivatives. So for instance, if we use the second derivative, we make what's known as the Taylor polynomial, we see that, lo and behold, we have a polynomial approximation, but our error is smaller. And of course, why stop at a quadratic? We can keep going further and further and further and get better and better approximations. So we say, hey, this is a great idea. Let's apply this to differential equations. The way that we do it is to say, previously, we started with the function we knew, and we came up with this Taylor polynomial or Taylor series and got a good approximation. Now we're going to start with a function we don't know. And many differential equations are really hard to solve explicitly, and so we don't know it. But what we can do is we can say, okay, let's take what we don't know, but find a way to approximate it by a polynomial in a similar way. Now, how do we go about doing this? Well, the key is finding coefficients, starting with the constant term, then the linear term, then the quadratic term, so forth and so on. So a few basics to talk about. We're going to think about our power series. You'll hear this from time to time. You should really think of whenever you hear the word series, just say, oh, you mean like an infinite polynomial? Yes, yes, that's how you should be thinking of it, a big infinite polynomial. So whatever you would think of a polynomial doing, just do that with series and you'll be good to go most of the time. And so we're going to use our summation notation. So you want to make sure you're comfortable with this. So this is a Greek capital sigma. Sigma starts with S. S for sum. You have to say where you're starting. We're starting at 0. We're going to infinity. Then you have this k. Usually it's sort of a dummy variable, but it says, okay, you're going to let k go from 0 to infinity, and so for each value of k you get one term. And now what does a term look like? Well, it looks like c sub k, which means some constant, x to the k. So k equals 0, we get c0. K equals 1, c1, x to the 1. K equals 2, c2, x to the 2, and dot, dot, dot. Dot, dot, dot is mathematical shorthand for, and the pattern continues. And so it's just, sum is just a way of putting it down and saying, here is explicitly what that pattern is. There will be some series that we're going to refer to from time to time. There's lots of series that we do know. Sine and cosine, we can do log, we can even do arctangent. But the two that you want to be comfortable with and that you might see for right now, is we'll start with some simple stuff. E to the x, which is the sum x to the k over k factorial, and 1 over 1 minus x, which is the sum 0 to infinity x to the k. Now, e to the x is true for all x. But 1 over 1 minus x only makes sense when x is small, smaller than 1. Now, the key idea behind everything we're about to do is this statement. So if you're only going to remember a few ideas from today, and there's going to be a lot of ideas, this is an important one. So it says two series are equal if and only if their coefficients are equal. Think about a polynomial. two polynomials are equal if and only if their coefficients match. So the constant terms match. The terms in front of x match. The terms in front of x squared match. And that's what that's saying. They might say, but how do we use this? Well, what we do is we're going to turn differential equations into big polynomials. And we say, okay, we've got a polynomial on the left-hand side, we've got a polynomial on the right-hand side. Let's compare. And we match up coefficients, and that gives us information. And in particular, the initial conditions help us give the start of the coefficients, and then this matching up lets us, as a series of dominoes, help us find the remaining coefficients, one after another. So we're going to be working a lot with power series. So there are 5 things that we want to be able to do. The 3 most important ones are the ones at the beginning, namely that we can do linear combinations. So if we have 2 sums, and we have some constant times the first sum, some constant times the second sum, we can put them together. Now, I want to point out something about these 2 sums that's going to be important. Namely, notice that before we combine them, we said their powers look the same. So they both look like x to the power k. The second thing was there was another part that lined up, namely their starts, where we begin. They both start at the same place. So their powers of x and their starts agreed, and then we pushed them together. Now, this idea, linear, that's not foreign to us. It basically says, oh, things can be nicely put together. We can break things up over addition, and we can bring in constants. And that's what we're doing. And of course, you should think of, well, what are sums? Sums are just lots of stuff adding together. So ultimately what we're doing here is just saying, we've got a lot of things adding together, let's just add them together in a slightly different way. That's what a lot of the power series manipulation is. Just say, hey, we have the same sum, let's look at it in a different way. Now, the next idea, I like to call it peeling. Now, this idea you'll find very appealing in that, what are we doing? It says, suppose you have a sum. Well, right now it starts at m, but you don't want it to start at m. You want it to start somewhere else, n, right? Well, usually we want n to be after n. We say, okay, no problem. What we'll do is we'll pull off the first few terms, and then we'll start our sum later on. So this peeling just says, oh, hey, we can grab our first few terms and pull them off. Now this lets us change our start. And that's an important thing to do. Because remember, to combine, and we want to combine, we need our starts to match. So peeling is how we get our starts to match. All right, now shifting. Now shifting, you should think of it a lot like substitution. And that what we'll do is we'll change the symbol that we use. So right now, I say, well, let's change it. So notice I have to the power k minus I. I say, well, I don't want k minus I, where I is number. It could be k minus 1, k minus 2. So I'm going to shift it. So I'm going to rewrite it where L is k minus I. And now I say, oh, that looks much nicer. But of course, if I change it in one place, I have to change it in every place. It's a lot like substitution when it comes to integration. If we make a substitution in one place, we've got to figure out where does it go every place. Well, there's the pieces in the sum. So for instance, this k, well, we can solve for k. K is L plus I. All right, so that's why this C sub k becomes C L plus I. But we also have to change our indices. Where do we start? Where do we stop? So right now, this goes from m to infinity. Well, that's for k. Well, now we say, okay, where does L go from? Well, where do you start? Put in k equals m, m minus I. Great. Where do you stop? Well, you stop when L is infinity minus I. That just means infinity. So these are the same things being added together. The only thing that's happened is we've just sort of rephrased it. That's it. We haven't added anything new. We haven't removed anything. We've just rephrased it. Now, what's going to happen with these first three steps? The linear, the peeling, and the shifting. You're going to use this a lot. So you want to be comfortable with these operations. Ultimately, what we want to do is put all of our pieces together into one sum. One sum to rule them all. So how do we do it? Well, step one, and this is what I want you to think about doing, is first off, do a shift. And you want to have all your powers of x have the same form. And so that's the key with your shift. So all powers of x have the same form. And it doesn't matter what you call it. I like to think of it as x to the L, but whatever your symbol is. All right, now after you've done your shift, the next thing is you check to see if you need to peel. Now, what does that say? Well, we just want to make sure all sums start at the same spot. Now, it's possible that on some terms you have to peel a little, some terms you don't have to peel anything. But we want to make sure all sums start at the same spot. All right, and then the last thing is you do your linear combination and you put it all together into one sum. And that's the idea. So we're going to be doing that over and over and over again. So you want to get used to these three steps: shift, peel, linear combination. Put it all together. Now I want to put a little asterisk here by peel, which is to say sometimes you can re-index if the first few terms are 0. So you can say, look, I know that when I plug in 0, I get 0. When I plug in 1, I get 0. So the first time I get non-0 is 2. Great. So instead of starting at 0, start at 2. Or start at 1, or stay at 0. Whatever's convenient. So we can always re-index if the first few terms are 0. And that's only to the place we can just pick anywhere where to start where we have either a 0 or the first non-zero. All right. So sometimes that helps us avoid a little bit of peeling, and that just makes things simpler. Ultimately, we want to keep things simple. You know, that's the goal of math. All right, we talked about the first three. Those are the three we're going to use a lot. We still have 2 to go. Now, one of them is derivatives. And we're going to use this a bit, because what we're going to think of is we're going to say, well, our solution looks like a series. So we need to know how to take a derivative. Well, how do you do it? Term by term. Okay, is that it? Yeah, that's it. Really? Yeah, really. We wouldn't lie to you. We're nice. We're honest. Okay, great. Now, the last thing we'll mention is multiplying. Now, here's the good news. Don't stress about multiplying. We're never going to do it full on all the way into what you have to do, which is to say, oh, you got to do this convolution of coefficients. We will be multiplying the starts of things, but for that, we oftentimes just say, look, just think of it as bits of polynomials, and we'll get what we need by just saying, carry out the multiplication. And ultimately, that's what this comes from. You just think about, okay, you have these 2 big series, and you just say, okay, what happens when we start multiplying at the beginnings? And that leads to this expression, which we call convolution. Now you might say, well, we heard convolution recently. We talked about that with Laplace transforms. Is there a relationship? In fact, there is. If you look at the way that the sum goes, think of a sum as an integral. In some sense, they really are doing the same thing. Sums and integrals are about adding things up. Okay, so if you think of this as an integral, we have one coefficient that's going up, while simultaneously the other coefficients going down, and that's what's happening with our convolution. So there is the reason we call it convolution. All right, well, that's a lot of theory. Let's go and do some practice. So let's start by practicing putting things together. We talked about our 3 steps. So we want to rewrite the following as a single power series. We have a sum from 2 to infinity, k minus 1, ck, x to the k minus 2, and a sum, k equals 0 to infinity, ck, x to the k plus 1. All right, what do we do? Well, we say, okay, first thing is shift, right? Shift, pill, combine. Those are our 3 steps. Shift, pill, combine is, by the way, what we call linear. All right, so we say, all right, we'd like to have everything look like x to the L. All right, so what do we do? Well, here we say, that's k plus 1. All right, so we'll let L equal k plus 1. Now here, k minus 2. L equals k minus 2. Okay, so this is, we're going to do them separately. So there's 2 separate sums. And so you might say, wait, I can't have L equal k minus 2 and L equals k plus 1. Well, I can, because there's sort of 2 worlds. There's this world, there's that world. And I do them separately. And so we're okay to do that. Now, when we do this, we say, okay, here, if L equals k minus 2, we can think of k as L plus 2. Now, what happens to our sum? Well, we have a sum, k, whoops, not k, first mistake, right? We're switching to L. L, there we go, L equals, now, if k equals 2, what is L? 2 minus 2. So that would be 0. And then if k is infinity, L is infinity. All right, k, that would be L plus 2, k minus 1, L plus 1, c sub k, c, L plus 2, and x to the k minus 2, x to the L. All right, that's the first sum. That's our shift. Plus, now here, L equals k plus 1. Okay, so sum. L starts where? Well, starts at 1, right? 0 plus 1 is 1. 1 to infinity. C sub k, well, what is k? L minus 1. So it'd be c sub L minus 1. Then x to the k plus 1 is x to the L. All right, so we've done our shift. So these sums here are the same. Now you might say, well, how can they be the same? This uses a k and that uses an L. But k and L are indexes. They just disappear when you write it all out. So what you can imagine what we've done is we wrote it all out and then we recompressed it in a different way. And so they are the same. They both represent the same set of things being added together. Well, now what do? We've done our shift. Do we need to pill? Well, do our starts agree? They do not. Notice this starts at 0, that starts at 1. So we need to pill. So we say, okay, we're going to pill off here, so it starts at 1. All right, no problem. So what do we get? Well, we say we're only going to pill off the 0 term, so that would be 0 plus 2 times 0 plus 1 times c sub 2 x to the 0. Okay, plus the summation. Since we peeled off the 0 term now, we start at 1. 1 to infinity, L plus 2, L plus 1, c, L plus 2, x to the L. And then that sum we're fine with. We didn't have to do anything. 1 to infinity, c, L minus 1, x to the L. All right, the starts now agree. Nice. So what do? We're going to push it all together into one sum. All right, we're at shift, pill, linear combination, so combine. All right, so we get 2c2 from this term here, plus our one sum. L equals 1 to infinity, because they both start at 1. And they both have x to the L, so I'm going to combine x to the L. And here we'll have L plus 2, L plus 1, C sub L plus 2, plus C L minus 1. And we're done. So we successfully wrote this as one single sum. Now you might say, well, wait, it doesn't feel that way. Well, sometimes the beginning can be a little weird, and you might have a few terms at the start which follow a slightly different pattern. That's okay. So you can pull them off and say, look, this follows a slightly different pattern at 0 versus 1 to infinity, but that's all right. It's still one single series. And so, great. See, this isn't so bad. Just follow the steps. Shift, pill, combine. Shift, pill, combine. You'll be fine. So now let's apply it to differential equation. We're given that y, which is a power series, sum 0 to infinity c sub k x of k, is a solution to y double prime plus xy equals 0. We also have some information. Y of 0 is negative 4, y prime of 0 is 3, and we're asked to determine C0, C1, all the way up to C8. Wow. Okay, so we're going to get a lot of coefficients here. All right, so what we're really building up is we're saying, you know, what does this function look like locally around 0? Well, what can we do? We can start by saying, hey, we're going to have to take a second derivative. So let's think about what happens in terms of our y. Well, that gets into our derivatives, right? So we know how to take derivatives term by term. So if we start with our y, we'll just rewrite it. So it's handy. Sum 0 to infinity c sub k x to the power k. Our y prime, well, again, term by term. K equals 0 to infinity, k, c sub k, x, k minus 1. Bring the power down, and then subtract 1 from the upstairs. And y double prime, well, that's the sum, k equals 0 to infinity of k, k minus 1, ck, x to the k minus 2. Right? Because the k minus 1 comes down, and then you subtract 1. So it's not k squared, it's k times k minus 1, x to the k minus 2. All right, so we have this for reference. All right. So what's next? Well, we're going to work on the y double prime plus xy equals 0. I want to point out one more thing. They gave us some initial conditions. Let's think about what that means in terms of our series. So let's start with y of 0. So remember, y is this sum. The sum k equals 0 to infinity, ck x to k. So when we plug in 0, which is negative 4, what happens? Well, you get a lot of terms that go away because you have 0 to a power. And so what doesn't go away? Well, the only thing that doesn't go away is the constant term. And the constant term is C0. So, like, what? We've already succeeded. We're 1/8 of the way there. Well, actually 1/9, because there's 0 through 8 would be 9 terms. We're 1/9 of the way there. Wow. And look at all this space we still have to work with. All right, well, how about y prime? All right, so y prime, well, again, we have this for reference. That's our sum, k equals 0 to infinity of our k c sub k x to the k minus 1. All right, well, plug in x equals 0, right? It's x, so what do we get? Well, y prime of 0, we know that's 3. Well, what's not going to vanish? Now here, when you plug in k equals 0, you get a 0, so that's gone. When you plug in 1, you'll get 1, c1, x to 0. Oh, well, that's just c1. Well, what happens if I plug in 2? 2, c2, x to the 1. Well, x is 0, so that's gone. 0. 3, c3, 0 squared, gone. All of the rest of the terms are gone. So now we've got c1. Nice. So it turns out our initial conditions are the first few terms in our power series. We're priming the pump. Okay, so now how do we get the rest? Okay, well, for the rest, we're going to actually turn to our differential equation. So, y double prime plus xy. What do we do? Well, we just say every term we're going to replace by a series. So we're going to replace the y double prime by a series. We're going to replace the y by a series. X is good to go because x is a polynomial, and that's essentially what a series is. So we say, okay, this would become y double prime. Well, that's our just copying sum k equals 0 to infinity of k minus 1, ck, x to the k minus 2, plus x, the sum, and now plug in y, k equals 0 to infinity of ck, x to the k equals 0. Well, let's see what this becomes. Now, we're going to do various things here, but one of the easiest things we can do is say, see how we have this x? Let's move it inside. All right, so we'll move our x inside. All right, so what do we have? Well, this would be the sum, k equals 0 to infinity of k minus 1, ck, x to k minus 2, plus the summation k equals 0 to infinity, ck, x to the k plus 1. This feels a little familiar. Let's pull back our last problem for a second. Here I happen to have it. Let's see, what do we have? We have a sum, k minus 1, ck, x to k minus 2, and a sum, ck, x. It's almost the last problem, right? And they're probably thinking, oh, Steve, oh, there's a 2 there, and there's a 0 there. But wait, look at this. What happens when you plug in 0? You're going to get 0, right? Because that'll be 0. What happens when you plug in 1? That'll be 0. So 0 and 1 are both automatically 0. So we can change this to 2, because that's actually the first time we get a non-zero, which means it's exactly what we've done before. And so what we'll do is we'll say, look, let's not reinvent the wheel. We'll replace the sum by this expression. All right, so we have, well, let me put this somewhere. This becomes our, whoops, sorry, I want to change colors here. Here we go, here we go. So by what we've done in our previous problem, and so we'll save work by not redoing it, this 2c2 plus the sum 1 to infinity of L plus 2 times L plus 1 C L plus 2 plus CL minus 1 x to the L, that's the left-hand side, equals the right-hand side, which is 0. All right. Now, our big aha Or if you're like, what needs to be true? We've got polynomial, because series is like polynomial, equals polynomial. So when do two polynomials match? When their coefficients match. So now we start saying, okay, that says what? Well, it says this coefficient, which is our constant, well, it has to match the constant term here. Well, that means that this will be 0. What about this coefficient, which is the coefficient of x to the L equals 1 to infinity? Well, that has to match the coefficient of x to the L over here, which is 0. And now we're like, oh, okay, so we can make a conclusion. We can now conclude that C2 is 0. Another one. Nice. Okay, all right, so C2 equals 0. Okay, so let's make our list here. So we've already said C0 is -4, C1 is +3, and C2 we just found was 0. All right, good. So we're a third of the way done. Now, the next pieces are going to come from here. So what does this tell us? Well, it really tells us we have relationships in our coefficients. And so we can rephrase this in the following way. Namely, we have that for L greater than or equal to 1. Now, why starting at 1? Because that's where the sum starts. We can say L plus 2 times L plus 1, CL plus 2, plus CL minus 1, just grabbing the coefficient, is equal to 0. Okay, well, let's plug in. Let's start with 1. What do we see? Well, we see 3 times 2 times C3 plus C0 equals 0. Well, do we know what C0 is? Yeah, we do. Well, so that says 6C3 minus 4 equals 0. So C3 is 4 over 6, 2 over 3. All right, nice. All right, so we'll add that. C3, 2 over 3. All right, how about L equals 2? What does that tell us? Well, it tells us 2 plus 2 is 4. 2 plus 1 is 3. C4 plus C1. Well, let's go ahead and just put in what C1 is. C1 is 3. All right, so plus 3 equals 0. Well, now we can subtract 3 over, divide by 12. Actually, we can just divide by 3 right away. And what do we get? Well, this says, aha, C4 is minus 1 over 4. Okay, great. So C4 is minus 1/4. And we keep going. And, oh, they asked a lot. Probably shouldn't have asked so much. But, all right, you do what you have to do, right? Okay, so L equals 3. We can get this as 5 times 4, C5, and plus C2, which is 0, equals 0. Okay, so 20C5 equals 0. Ah, that's nice. C5 equals 0. Okay. Good. Well, L equals 4. We have 6 times 5 times C6 plus, now we're going to plug in C3, so that's plus 2/3 equals 0. Okay, subtract 2/3, divide by 30, and we get that C6 will be -1 over 45. All right, so C6, -1 over 45, and almost finally, L equals 5. We'll get 7 times 6 times C7, and now add in C4. Okay, that's negative 1/4. So minus a fourth equals 0. And so C7 is a number. Well, 1 over 4 times 6 times 7, which is what, 168? All right, I'll believe you. You seem trustworthy. All right, so C7 is 1 over 168. And then the last one, L equals 6. 8 times 7 times C8. And then we're going to add C5, right? Well, what's C5? 0. That has to equal 0. Aha! So C8 equals 0. Well, we ran out of space. C8 equals 0. Okay, there we go. Whew. Almost made it. Almost made it. And so that's the idea. Now, normally we don't go this far, but, we should do it once. Now, sometimes I will point out that you can rewrite the expression here. And so we ran out of space on this page, so let me grab another piece of paper here and explain what I mean. So this term here, we've said for L greater than or equal to 1, L plus 2 times L plus 1, CL plus 2 plus CL minus 1 equals 0. Well, what we can do is we can rearrange that. So we could say, well, that says L plus 2 times L plus 1, C sub L plus 2 is minus CL minus 1. And in case you're wondering where we're going with this, the key here is we're solving for that term. All right, well, so CL plus 2 is minus CL minus 1 over L plus 2, L plus 1. All right, now that's for L greater than or equal to 1. Well, maybe we say, okay, let's do a shift, because why not? We can do that. And so, well, we can say, let's let n equal L plus 2. Sure. So if we do that, well, this says Cn equals, now, what is L minus 1? Well, to get from L plus 2 to L minus 1, we'd have to subtract 3. So this is minus Cn minus 3. L plus 2 is n, and L plus 1, well, I'd subtract 1 from both sides, is n minus 1. And this is, well, when is it true? Well, it starts at L equals 1, so 1 plus 2 is 3. And this is for n greater than or equal to 3. So sometimes when you hear recurrence, this is how we'll think of it, that the term Cn is written in terms of the previous. In fact, in this case, you go back 3 and you divide by n over n plus 1. Now, for my purposes, I'm fine with either one. So whichever one you want to use is great. But just keep in mind, there's both ways to think about this. And then once you have it in this form, you just plug away, just like we did already. All right, so that's the big idea. We're going to do this several times. And hopefully, after we do it several times, we're going to get really good at it. So the technique that we just found will oftentimes be called finding a recurrence relationship. So what do? Well, we know from initial conditions we'll get a few terms. Now it depends what we start with. If we start with the first order differential equation, we'll only be given y of 0. That'll give us a constant term. If we start with the second order differential equation, we'll have y of 0 and y prime, which gives us the first few terms. A third order differential equation will give us the next few terms, and so forth and so on. You should be careful here. We'll almost always do first or second order. So y is 0, y prime is 0. Y double prime is 0 is not quite C2. You have to divide by 2. If you're saying, wait, where did that divide by 2 come from? It's the same divide by 2 that shows up in Taylor series. So That's what's going on. So you should think of this as divide by 2 factorial. This was divided by 1 factorial. This was divided by 0 factorial. All right, so what was our process? Everywhere where we saw y, we replaced it by our series. Now that included y prime, y double prime. If you have any functions of x, you rewrite it as a power series. Now previously we just had x by itself. That is actually a series. It's a polynomial. So polynomials were fine. Once we replaced everything in some form, we put it all into one sum, right? Remember, one sum to rule them all. And after we have that one sum, remember though, it's not just a matter of like, aha, I'm just going to ignorantly put it into one sum. It's one sum where it's x to the power L, or x to the, whatever symbol you like. But it's x to the power. You're gathering your coefficients. That's what's actually going on. When we say put it into one sum, we're really saying gather up your coefficients. That's the idea. And now you say, hey, the recurrence relationship is found. Look at your powers of x. And you have to make sure they agree on both sides. Usually, if you have something equals 0, it's set it to 0. If you have something equals something, you say the coefficients on both sides have to match. This gives relationships, and so we get what are called recurrence relationships. Recurrence says I'm looking back at something to figure out my current state. So if I say, oh, in our previous problem we said, hey, C6 depended on C3. So I'm looking back at C3 and using that to help me figure out C6. So that's what we mean. And now we use that to find as many terms as we want. Now, keep in mind that when we put things into a single sum, there may be a few exceptional things at the start, but other than the few exceptional things at the start, we'll have that machinery of the recurrence relationship that finds our remaining terms. All right, so that's our big idea number 1. Push everything into one sum, figure out what's the coefficients of powers of x. That gives relationships between coefficients, which we call the recurrence relationship. And we can use that with some initial conditions to get as many terms as we want. There is a big idea number 2, which says sometimes we don't care about the recurrence relationship. The problem will just say, find the first few terms. We say, great, we can do that. And that actually can be faster because we can say, look, we don't need to know everything about the whole sum. We don't need to go all the way to infinity. We just need to go enough, far enough out to figure out what our missing terms are. If we want to find, say, up to C4, the coefficient of x to the 4th, we say, okay, how far do we need to go? Now, there's a good rule of thumb, which is when we look at the differential equation, every term in the differential equation, so the constant term will give us a new coefficient. What's in front of x gives us a new coefficient. What's in front of x squared gives us a new coefficient, and so forth and so on. So we have some coefficients from initial conditions, and then we say, how many more terms do we need to look at to get what we need? We'll see an example of this. We say, okay, now once I know how far I have to look, I'm going to replace y and any functions of x by just enough so I can look at those pieces, those terms. And now I do my expansion and I do my comparison and I say, great, that helps me get my coefficients. Life is good. Now, this works pretty well if you have things which are unwieldy functions to work with. And so let's see an example. So let's look at an example of this sort of second idea. We're given that y is a series solution to this differential equation, y double prime plus y squared is e to the 4x. And we have some initial conditions. Y of 0 equals y prime of 0 equals 1. And we're asked to find C0, C1, C2, C3, C4. Okay, notice we don't need to find a recurrence relationship. And we're like, whoo! Okay, because recurrence relationships can be tricky. And when you have something like y squared, it would be trickier, because that would be really, it's two big series multiplying together, convolution, not fun to deal with. And so we're going to avoid that. That's all right. We don't have to find a recurrence relationship. We just have to say we only need to go far enough to get our terms. Now, when we think about this problem, we say there's two things going on for these coefficients here. So what are they? Well, first thing that's going on is we have some initial conditions. And so two initial conditions gives us our first two terms. All right, so let's talk about those. So we have C0, C1. These are going to come from our initial conditions. Now, what do we know? Well, we know we have y of 0 is 1. Now, y of 0 is C0, which is 1. And we have y prime of 0. Well, that's C1, which is also 1. All right, so we get two terms from initial conditions. The other, which is to say everything else, has to come from somewhere else. So we have C2, C3, C4. Where are those coming from? Well, that's going to come from the differential equation when we plug in and put everything in terms of x. And in particular, the rule of thumb is every term gets us a new constant, right? So what does that really say? C2, this says look at the coefficient of 1. So we're going to look at the constant term on both sides. C3, well, that's going to come from the coefficient of x. C4, no surprise, that's going to come from the coefficient of x squared. So the moral is we only need to look up through x squared. And once we do that, we'll have enough to figure it out. So now we're like, nice. Okay, so here we go. Let's talk about our terms. Now, what about y double prime? Now, we know how y starts. C0 plus C1x plus C2x squared plus C3x cubed and C4x to the fourth. Now, there's a reason I'm going up through x to the fourth. I'm going to take two derivatives, and every time I take a derivative, I knock powers down. I want to make sure I get up to at least the square. So that's why I'm stopping at x to the fourth, so that when I take my derivatives, so first derivative being C1, 2C2x, 3C3x squared, 4C4x cubed, and second derivative, which is 2C2, 6C3x, and 12C4x squared. All right, so we now have our y double prime. For y squared, we only need to go up through the quadratic term, C0, C1x, C2x squared. And then e to the 4x, well, we know what e to the 4x is, right? We have a whole series for that. And maybe we'll do a little note here. E to the 4x, well, that's the sum, 0 to infinity, of 4x to the power k over k factorial. Now, when you put in k equals 0, 4x to the 0 is 1. 0 factorial is 1, so that's 1. Put in k equals 1, 4x to the 1 is 4x. 1 factorial is 1, so plus 4x. Put in k equals 2, 4x squared would be 16x squared, but we're divided by 2 factorial, which is 2. So that's 8x squared. And now we have up through the squared, dot, dot, dot. Okay, so we're going to put all of this information together, and we're going to plug it into our differential equation. So here we go. We have y double prime. So that's 2c2 plus 6c3x plus 12c4x squared plus dot, dot, dot. So we're going to keep the dot, dot, dot. That's just our way of reminding ourselves And there's other stuff, but we're not going to worry about it. So here is our y double prime. Okay, then we're going to get y squared. So that's y times y. So everything gets in terms of x. C0, C1x, C2x squared, dot, dot, dot. There's a y. C0, C1x, C2x squared, dot, dot, dot. There's another one. Okay, so there's a y times a y, and there's y squared. And all of that is going to be equal to our 1 plus 4x plus 8x squared plus dot, 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 which is our e to the 4x. All right, great. Now we just have to do a little bit of cleaning up. Okay, so our big job right now is going to be what happens with this part. Okay, what can we do? Well, let's use what we know. We already know C0, C1, so that makes it a little bit easier. We have that these are 1s, and we say, okay, So we could take 1 plus x plus c2x squared plus dot, 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 times 1 plus x plus c2x squared. Well, okay, let's start with constants. How do you get constants? Well, the only way to get constants is 1 times 1. All right, how do you get x? Well, you could take an x and an x, right? 1 times x, x times 1. So that's 2x. Okay, how about x squared? Well, 1 times c2 plus 1 times 1 plus c2 times 1. Notice how we're going in opposite directions? That's the convolution happening. So we get c2 plus 1 plus c2. So we could say that's 2c2 plus 1 x squared. And then we don't care. Dot, dot, dot. You know, that's the nice thing. We only need to get up through x squared. All right. So all of this together, here we go. We get on the left-hand side, what's our constants? Well, we have 2c2 and plus 1. All right, what's our coefficients for x? We have 6 times c3 plus 2. X. What's our coefficient for x squared? 12c4 plus, now here it's 2c2 plus 1 x squared plus dot, dot, dot. Now, so this was gathering the coefficients for 1x x squared on the left-hand side equals, of course, the right-hand side. 1 plus 4x plus 8x squared plus dot, dot, dot. All right, so we're ready. We're playing the matching game. So we match. The constant terms have to match. So 2c2 plus 1 equals 1. What does that tell us? Well, you can subtract 1, divide by 2. C2 is 0. All right, progress. Okay, 6c3 plus 2 has to equal 4. All right, so 6c3 plus 2 has to equal 4. What does that tell us? Well, that tells us c3, you subtract 2, would be 2, divide by 6. 2 over 6, or 1 over 3. All right, great. And finally, 12c4 plus 2c2 plus 1 has to match with 8. All right, so 12c4 plus 2c2 plus 1 equals 8. But we know c2 is 0. Okay, So that goes away. We subtract 1. 8 subtract 1 is 7. C4 is 12, C4 is 7. So that tells us that C4 is 7 over 12. And we're done. All right? Because we've got C0, C1. We have C2, C3, C4. So, all right, maybe let's put them all down here in a corner just so that they're all together. It's nice to put them all together. So C0 is 1, C1 is 1, C2 is 0, C3 1/3, C4 7/12. All right, nice. Okay, now you know the big ideas, and you're actually surprisingly a good chunk of the way there to understanding how to work with series. Most of the rest of what we're going to be talking about are things such as radius of convergence and more examples, but you've got the basics down. All right, good. Big polynomials, you just work with them, put things together, and life is good. All right. Bye. You're still here? All right. Well, since you stuck around, I'm going to actually show you kind of a third way to do it. I would not encourage you to go this way, but I just want to point out something that you could have done. So let's look at this problem and do it in a different way. So this third way, again, it's all about saying, let's find the first few terms, but there's some subtleties, and so be careful if you use it. All right, so we're going to cover this up. So we're going to try to figure out what's going on. All right, so what are we going to do? Well, we're going to use the differential equation to help us find a recurrence. I know this sounds weird, but bear with me and we'll understand it in just a moment. So we have y is the sum, k equals 0 to infinity, ck x to k. Now, I'm going to call back for something from Calc 2. Namely, we have Taylor's series. So k equals 0 to infinity. And now what happens? You are going to take the kth derivative at 0 over k factorial x to the k. All right? So what is this saying? What it's saying is if you want to find the coefficients, ck, you just have to find the corresponding derivatives. You might say, well, yeah, but how do we do that? All right, here we go. We know we have y of 0 is 1. Y prime of 0 is 1. And where do we get y double prime? Look at that. We have that y double prime plus y squared equals e to the 4x. Or you could say, hey, y double prime is e to the 4x subtract y squared. So let's plug in. So according to this, y double prime of 0 is equal to, well, e to the 0 subtract y of 0 squared. But e of 0 is 1, y of 0 is 1, and so 1 minus 1 is 0. Haha! Well, that's fine. That's y double prime. But how are you going to get y triple prime? Ah, that's what you're thinking, right? You're like, ha, Steve. No problem. Here's what we'll do. Start with this relationship, and let's turn the wheel by taking a derivative. So we get y triple prime, derivative of e to the 4x, 4e to the 4x, and then we're going to get derivative of y squared, which is 2y prime. Okay, so according to this, y triple prime of 0 would be 4e to the 0 minus 2 y of 0 y prime is 0. Well, okay, well that's 4. Y of 0 is 1. Y prime of 0 is 1. So minus 2 times 1, which is 2. All right, well, wow, that's great. But we still need one more, right? Because if we're going up to the 4th term, that's like going up to the 4th derivative. All right, we can do it. What do? Well, we take another derivative. So we get y 4th derivative. Well, normally we would probably just put a 4, but what would that be? 16 e to the 4x and minus, now here we have to use the product rule, so it'd be 2 y prime, and go to the first times the second, and then minus 2y, y double prime. All right, so our 4th derivative at 0, okay, would be 16 e to the 0, subtract 2, y prime of 0 is 1. So times 1, y prime of 0 is 1, and then subtract 2, y of 0 is 1, and y double prime of 0 is 0. So times 1 times 0. Okay, well that's 16 minus 2 minus 0. That's 14. All right, now, how do we get our coefficients? Well, our coefficients are, we divide by k factorial. So C0, we're going to divide y of 0 over 0 factorial, which is 1 over 1, which is 1. C1 is y prime of 0 over 1 factorial. That's 1 over 1, which is 1. C2 is y double prime of 0 over 2 factorial. Well, that's 0 over 2, which is 0. C3, well, that's y triple prime of 0 over 3 factorial. Well, that's 2 over 6, 1/3. And C4, well, that's the 4th derivative at 0 over 4 factorial. Now, what does that turn out to be? Well, 4th derivative is 14. 4 factorial is 24. And if you divide 14 by 24, you get 7/12. And you can keep going. So you can take derivatives and keep running this machine. So take another derivative, you get the 5th derivative. That gets you, plug in 0, gets you the 5th derivative at 0, and so forth and so on. And if you check, look, 1, 1, 0, 1/3, 7/12. It also works. So you might say, wait, how is this working? Well, what's really going on is that your differential equation is the basis of the recurrence. And so you're taking derivatives to help get to your next term. And why do I discourage it? Well, you have to remember that, you know, when you plug in and you find the derivative, you also have to divide by a factorial. And but you know what? If you like it, that's great. If you don't, you can forget it. That's all right too. All right, well, thank you for sticking around and saying, there's lots of ways to do things, isn't there? Isn't that cool? All right, well, this time we'll see you again.